So thank you, Pierre. I'm impressed to be here to talk about this free last year. That was a PhD conducted under the supervision of Fabien Gondon, Catherine Faron, and Franck Michel and Anna Abiakel. And this work was focused on how can we try to extract knowledge from text into directly into the linked open data. So the starting point of this thesis was, of course, Wikipedia, and from the other hand, also DBpedia. And as you know, DBpedia is based on the extraction of the structured data that you can find on the top left of Wikipedia. And we still have a lot of text and information that is not covered by DBpedia. So my PhD research question was the following one. Can we learn effective, and I want to emphasize it, customize extractors targeting specific RDF patterns using both Wikipedia and DBpedia? So we follow during this last 3 years an iterative research plans that started first by trying to understand what was the state of art after and just during the transformer era, let's say. We then try to understand how can we formulate on how the task formulation is impacting the generation of triples, focusing specially on the case of the data types properties. Then I try to find a way to systematize how can we do pattern-based relation extraction from a dual base and integrating into it human in the loop. And finally, the last goal of this thesis was to be able to extract both data type and object properties. So we started with a systematic literature review that you can already find in the early version on arXiv, let's say. As you know, a systematic literature review is really long work. You have to read a lot of paper. And for example, as you start a PhD in the relation extraction domain, you have faced 2 Google Scholars, and you can find more than 4 million of articles talking about this topic, which led us in our team to develop the tool which is called SHACL, and which could be used to spark systematic literature review. So it allows us to collect papers from diverse digital libraries, to collect them and to also push them into Zotero with a base of a notation related to these papers. And using these tools, we were able to conduct 3 different collections on different dimensions. First, we focused on surveys published in the domain related to relation extraction. We also focused on datasets and then about the models. So we follow a classical Prisma workflow, and we define in this objective a really fine analysis grid, which is covering more than 43 dimensions. And from this survey, we obtained a lot of insight, let's say, and we were able to highlight the fact that transformers completely emerged overwhelmed the research production related to relation extraction. So I don't want to remind you what is a transformer, but you know that you have this encoder. You can use it by using only the encoder blocks to try to embed text. You can also use a decoder to generate text, and you can also use both blocks, which is the case in the use of encoder decoder, which is good at both understanding and generating. And this is a model that was used heavily for translation. And we were able to completely see this change by studying the papers. We were before it using a lot of encoder specialized models. That's now, since GPT, a lot of researchers propose and prefer to use encoder decoder models as well as decoder one. And we completely shift finally the way to do relation extraction, where we were before doing using pipelines to first extracting entities, identifying relation, classifying relation to obtain relational graph. We are now able to do directly text to graph generation. And this is something that we can find back into the dataset as the majority of the datasets are made to solve the relation classification task. Another thing that we saw by doing this analysis is related to the fact that a lot of research papers doesn't deliver any information about the cost of the experiments. On the hundreds papers we analyzed, we had only 10 papers explaining finally what was the cost of the experiments, which is a bit afraid in that way. And aside that, we were also able to face the fact that datasets since the 5 last year are completely driving also aside the architecture, right? The research. So we can still find we were able to underline the fact that we have already a lot of saturated benchmark, but we also have still challenging research questions related to some data sets related to few shot learnings, but also specialized domains. And we can find also in this challenging data sets still data sets related to relation extraction from documents. Okay, in our perspective, we underlined 3 gaps in the literature. We saw that existing models do not generate RDF relation directly. We were also able to highlight the fact that dataset proposals were mainly built from a knowledge graph on Wikipedia. And finally, these objects, these dataset are, let's say, flattening for resolving the relation extraction task by losing a lot of semantic grounding. And finally, we also underline the fact that very few methods target specific parts of the ontology at that moment. So which led us to this second research question: which aspect of the task formulation could impact the generation of triples with data types properties? We chose to focus on data types properties because until here, all the methods were more focused on the extraction of objects, and we was thinking that it was a good start. So what is shape-based relation extraction? This is about having a text in a site, having in a site, but also shapes, and to use theirs to constrain models to produce from them relational graphs. So why using small encoder-decoder models rather than LLMs? That's a question that I had to answer a lot of time during my PhD thesis. First, we know that it is cheaper to fine-tune and faster in inference, which could be really important in really intensive production lifecycle, right? They better deal with context inputs, and they also produce fewer hallucination. And finally, they are also easier to audit, and they allows data sovereignty. And as we have here SHACL shapes, we have also the opportunity to validate our generated graph using the SHACL shapes. So what is a SHACL shapes? So that is a set that is a set of properties and constraints that you define focused on the tipped object. Here we focused in our experiment on DBO person, which is representing already 1/6 of DBpedia, right? And we can define in these shapes which properties are optional, like this one, right? But also which one are mandatory, like the birth date, the birth year for person, but also the labels, right? And you can also define some logical arguments like here. So we focused on this SHACL shape, which is defining which properties we want to extract related to a DBA person. So now we have Wikipedia, we have a targeted SHACL shape. How can we train now an encoder-decoders to extract a relational graph? As you may know, they are not fine-tuned to speak Sparkle, right? To speak Turtle, right? Or any RGF syntaxes. So all the objective of this first research question was to find which linearization on how to write a graph to be represented as a sequence of text. So to conduct these experiments, we sampled data, graph, and text from DBpedia. And we also focused on comparing 13 different syntaxes related to that could allow us to represent RDF or triples. So in the literature, they heavily use two syntaxes that have a list on the tags one. But as you know, in the semantic web community, we are using W3C standards as RDF XML, Turtle, and triples JSON-LD. Aside from it, we also propose another syntax, which is light turtle, let's say, where we don't declare the prefixes, and we also omit to write these prefixes into the triples. Aside from it, we also try to propose some variation about how to write the triples. You can write them using using factorization, but you can also write them using multi-lines. That's more detailed, but it could maybe count at the end. You can also write them by factorizing them and writing them on the one line. And we also propose this factorization to both the list, the tag syntax. Right. And finally, we also propose a turtle ultralight syntax, which is completely omitting the 2 points that you have before the object. To conduct our experiments, we follow a cross-validation process where we are using also rotating random examples for the test before also the training and the validation, which allows us at the end to evaluate if we are overfitting, right? And as baseline, we use different models, which are encoder-based models, which are BART T5, PILE T5, FLAN T5, and COD T5. All of them are pre-trained differently using different strategies. They are trained also by using different training sets, and they are representing differently the sequence of text. We also propose to add all the specific syntax tokens specific to the syntax into the model before the fine-tuning. And as you can see, the syntax have already big impact on the numbers of tokens that we need to use to represent a sequence of triples. As you can see here, for when we use a total ultralight syntax, we are using 2 times less tokens than using XML syntax. And finally, how we evaluate that, we use the F1 macro and micro. We also computed the rate of parse triple at the end. We also computed the rate of write-rewrite choice for describing the subject. And finally, we also computed the rate of graph validating the SHACL shape we defined initially. And also something important, we also computed the carbon cost of each experience. So when we fine-tune an encoder-decoder models, that doesn't necessarily lead us to models that is able to write triples. We have the example of PILE T5 and FLAN T5 that was even fine-tuned, unable to produce any RDF syntax. We saw that COD T5 was able to produce some of them, but this model was also failing in a lot of times. Aside from that, we underline 2 challengers, which are T5 and BART. So here you can see the training time that needed each models to be fine-tuned, but also the performance here. And we underline from basic experiments 3 interesting syntax. We have T5 JSON here, which is really powerful, but that needs a lot of training. We have here BART using the text syntax, but we have also here BART using turtle-light syntax, which is closer to the semantic syntaxis one. So from this first research question, what do we learn? We understood that the choice of the model of the output syntax are completely essential. We needed 100 minutes for fine-tuning T5 using JSON. When we we needed only 10 minutes of training for fine-tuning our BART plus satellite models. Finally, we saw that our BART plus satellite configuration allowed us to obtain RDF output that are always passable, that are always choosing the right subject URI, and that always validating the SHACL shape. So how can we now try to system that approach to use SHACL shapes over dual knowledge base composed of both texts and triples? And how to do that using human in the loop too. So in our last experiment, we demonstrating that our methods allow us to obtain output that always validating the SHACL shape. But we also had the intuition that finally training a model based on this statement may also promote hallucination in text that does not convey a mandatory property. So for this reason, we relaxed a bit our frameworks by our task formulation by defining an initial shape, which is called now the maximal shape or the optimal shape we wanted to obtain. Aside from it, we select training examples containing at least one property of a maximal shape, and we now compare the list of properties generated with the one expected rather than using SHACL validation. Even if we can still SHACL validate our trippers obtained at the end with SHACL. So this is in this context that we propose Kastor, which is a framework for extracting conducting pattern-based extraction directly from a dual base. So it is composed from a first step, which is called the knowledge distillation. In this case, we have now our dual knowledge base. We have our shape that will allow us to construct, to build an initial knowledge graph focused on this shape. So I already presented you the shape that I wanted to focus on, the DB person. Aside from it, we are in the DBpedia environment, and we are missing a lot of trippers that could be inferred. So we also define a step which is called the root augmentation. And in this case, we were missing a lot of def year that could be inferred from birth dates and death date, and we materialize these trippers using SPARKLE constructs. From it, we obtain a distilled knowledge base, and we have to align them with the Wikipedia articles. And for that, we use something we call the wiki check, which is simply verifying if we can find the information into the text. Okay, so now we have a solution to distill a knowledge graph. Now, how can we integrate human in this loop? So we can now use our distilled knowledge graph to sample data to train and fine-tune a model. Aside from it, we can also sample data from it to test this model to obtain errors. We will obtain from that two types of errors. You already know the false positives that are trippers generated but not expected. In this case, the annotators will be asked to add the false positives that are expressed by the text into a corrected dataset. Aside from it, we have false negative that results from the distance supervision method we use. And this is all about trippers that were expected but that are not expressed finally into the text. So in this case, the annotators have to delete these trippers from the corrected dataset. So now we obtain from these two test sets two corrected datasets. The first one will be used to train a model on gold dataset, validated one. But I wanted also, in this moment, to verify if our task rule formulation was finally impacting or improving the result. So that's why I also sample a training set where all the training examples are validating the maximal shape we defined. And then, finally, from the second corrected dataset, we are able to test each of our models. We will obtain errors, and we will ask once again to our annotators to correct them. From it, we will be able to evaluate how much our models are able to discover facts that weren't available into our initial knowledge base. And what can we see from all these experiments? First, we saw that the task design largely improved the performance of the model, mainly by avoiding hallucination. So our intuition was true. And aside from it, we saw that by annotating and integrating human in loop in a light active learning way, allows us to obtain a model that could discover new facts, which is really interesting. So from this third research question, we proposed Kastor that allows to build pattern-based extractors in synergy with a knowledge graph. We also propose a new task design that allows to reduce the hallucination. And finally, we underline the fact that human annotation helps to complete a knowledge graph with relevant new facts. So we have now a first framework, which is working well on data type properties. So we have now to generalize and to be able to extract both data type and object properties. But by coming to this research question, we also understood that we have to also solve another research question, which is related to the fact that we have into DBpedia a lot of underrepresented properties, and we will have to generalize over them. So now, as we want to extract also object properties, I extended my initial shape with three different new object properties, which is related to the nationality, the birthplace, and the birthplace of person. I also adapted the rules and integrated new rules to infer missing data. For example, the country related to death place, but also the nationality in terms of country when I have citizenship related to that property. And finally, to be able to align our graph on trippers, I'm proposing now to use the markdown simplified version of Wikipedia articles, which allows us to also verify if our objects are present into our hypertext link, right? Okay, so now we have we have a brand new frameworks that allows us to extract also object properties. And we wanted to verify several hypotheses. First, as we wanted to compare if the object properties and the data properties impact the performance of our extraction, we propose first to sample train test set and training set, which is containing at least one properties of the set other shapes related to object properties, but at least one property, one data type properties. And aside from it, we had also this question related to the potential memorization effect of our model. We know that BART was pre-trained after 2021. So for this reason, we select only articles that were created before this date. So in this context, we had also a new experimental grid, which is now focusing on using Markdown articles, but also plain abstracts. And from these two different inputs, we focus now on a different subset of the optimal shape, which is focusing only on data types, object properties, and the complete shape. And as usual, we use cross-10 validation evaluation. Yep, and from that, we obtain a pretty satisfying results, but we can also underline that it seems easier to extract data types properties. Aside from it, we were, from these results, not really able to distinguish why we obtain more or less the same result from plain and Markdown abstract. So for this reason, we had to define some metrics that enable us to fairly evaluate how we are performing on object properties. I won't have the time to discuss it, but you can find all these details in the thesis. So now we compare ourselves we compare ourselves only on a simple context. We now have to compare ourselves with baseline. And that's why we first proposed to compare our result with Rebel, which was the state-of-art challenger at this moment. So for doing it, we had to reduce the shape on which we were focusing, because Rebel isn't able to extract all the properties as shown you in the optimal shape. And from the same baseline, we propose to evaluate both Rebel and Kastors. We use specifically plain abstract for comparing both models, and we can see from these results that we are doing better with smaller models finally. But we still have this problem to solve. We have large variance over our results. Why? Maybe that's because that we have rare property and common property in our shape set. So to verify this hypothesis again, we divide our shape into two new subsets, one containing all the frequent properties and the one containing all the rare properties, and we fine-tune a model of it. And when we have a look on the results, we completely agree with the fact that rare property drive the variance. So how to perform on this rare property? This is the second sub-research question related to this last part. How can we deal with underrepresented properties? So in this section, we finally first investigating by using classical machine learning strategy, and we then follow theory, let's say, which is related to something called the sufficient exposure strategy. I will detail it later. So first, how to compare ourselves and how is performing this the classical machine learning strategy. So we have different ways to improve our results. First, by oversampling array data, by also scaling the dataset, the training dataset by a factor of 2, 4, 10. We can also use stratification strategy, White-Hitler strategy, and to compare it, we fine-tune a model once again in this context. But how to evaluate them? For evaluating them, we simply propose also to evaluate these models using different test sets. So the first one is oversampling the common properties. The second one is oversampling rare properties this time. The third one is, as we did until here, composed of random evaluation set. And finally, the last test set is composed of articles published after the 2020 date. So what we can see from these results, we don't have any significant improvement, which is a bit frustrating. But we can see that our models is able to generalize the extraction of a new Wikipedia article. So that's a good point. But we didn't solve really our initial question, which is how can we perform over this rare property? And we follow this direction, which is related to tutorials that presented Alan Su at ICR 2025, which is demonstrating that for memories, which demonstrated that for memorizing given fact, we have to expose it number of times, which is at least 1,000 times during the fine-tuning to retain a fact. In our context, we don't have to retain a fact. We want to extract property triples. So maybe that our models need also to be exposed to a property at least 1,000 times during the fine-tuning, and we have to verify it. So to verify it, first, we took a look on our dataset, and we can see that the alias properties could be considered in our case as rare properties. We don't have enough training examples. So how can we have at least 1,000 examples of this property? We can use all the distilled knowledge graph, which is the first strategy we use. We can also try to use synthetic data augmentation. We implemented two naive synthetic data augmentation techniques. And aside from it, the last strategy is to ensure that the sufficient exposure is reached for each property. And from this different configuration, so to evaluate this different configuration, we use also a corrected version of a random dataset to fairly evaluate them, considering the fact that it could still have some noise in the DBpedia corpora, right? And from this view, what we can see that the only configuration which is able to improve our results is the one satisfying the sufficient exposure. So when we have a look on the detail of the performance of the other properties, we can see that this is the only model which able to perform on the rare property, the alias, the birth name, or the nationality. So what can we conclude from this last part? Well, we show that it is possible to conduct extraction from both data types and object properties. We also show that BART pretending data are not memorized during the fine-tuning. We also saw that our small and light models can compete with Weber. And we also understood that it is essential to take care of the exposition of each property to extract all of them. Okay, is it finished? Not really. Finally, we just use until here a really small shape, which was really simple. And we have in text to KG domain this benchmark that was proposed on the base of WebNLG, and which is focusing on 19 different shapes of ontology, let's say, on describing different class of DBpedia. So in our case, we use all to SHACL to transform all these ontology fragments into a SHACL shape, right? And we use our Kastor distillation process for obtaining a given set of a set of text and graph align with each SHACL shape. And we can compare to text to KG benchmark. Our method allows us to obtain richer text, which is focusing also on object properties. That wasn't the case of the text to KG bench. Aside from it, we have also a benchmark that arrived also related, and that was published by Lettre II, but this one is not open. So if you want to reuse our knowledge graph, this one is already available on Zenodo. So what about the performance? When we test our Kastor's fine-tuned shape-based extractors on the Kastor's test set, we can see that we have a pretty satisfying result with still this problem of variance of our results. So to be really effective, we will have to augment the examples related to the rare property inside these shapes. And finally, if we compare ourselves with the text-to-KG test set, we can see that we are, in a lot of cases, better than the LLMs that baseline that was proposed, which is pretty satisfying. So that's a lot of experiment that was conducted just at the end of my PhD. But from this first experiment, we can see that our method is have some advantage about when comparing it to state-of-art models like Rebel and also with LLMs. That our custom models are entity-centric. They are focusing on a SHACL shape that could be also adapted. The hallucination rate is really low compared to all the other methods. We could completely follow the potential data leakage, and we directly obtain from it RDF outputs at a really low inference cost, which could be really interesting. So all the models that was developed during these last experiments are today available on Hugging Face. Also, all the codes, all the knowledge graph we use for conducting our experiments is both available on Zotero, but you can find also all the codes related to the experiments on the GitHub, of course. So what can we do, or can we say about all the research questions we define? First, we propose a comprehensive survey offering a detailed overview of a field. And we also propose a tool, Silex, that could also allow us to conduct systematic review using paper with code, but also all the available digital library. Aside from it, we demonstrate that light syntax and light models enables efficient and resource-friendly relation extraction. We saw that Kastors could systematize pattern-based extraction using human feedback. And finally, we're demonstrating that the generalization of our method on proper solution for extracting shape could be done by satisfying and by verifying that we have enough examples of the rare properties. So what can we say after all this PhD? We answer a lot of research questions, but we still have a lot of research questions that emerge from it. Can we generate good quality shapes at scale? How to deal with long documents? How to deal with multi-language documents? How to create also synthetic data using shapes to produce graph and text pairs? And also, how can we integrate the small models into an agentic pipes or into agentic pipelines? Today, I'm also working on different research questions related to it. How can we translate a shape from SHACL to shapes? I think we also need a real benchmark about SHACL, Yago, DBpedia, and Wikidata. And we need, of course, interfaces for managing all this shape into a knowledge graph cycle. So today, to continue my work on my path, I'm actually postdoc into the ST Lab, where my research project is actually to develop shape contracts in the context of cultural heritage context. So that's all for me. I hope that this presentation feed your thoughts, let's say. I have to thank also Pierre and the Guardians to invite me to talk about it. And now I'm waiting your question, and I'm looking forward to the discussion. Thank you.